All right, we're going to be looking at another net change problem, but this is going to be a table, so we're going to have to approach it just a little bit differently as we go and solve it. Let's read the question together. It says the measured acceleration of a car. So I just want to go ahead and underline that word acceleration. So this graph is the graph of, table is the table of acceleration. All right, so the acceleration of a car at different times in seconds is recorded in the table below. So let's think about this for a second. For example, at time t equals 0, the car is accelerating at a rate of 6. Now, you could say feet per second squared. You could say meters per second squared. In this case, we're going to be using meters. And so the units down here, I'm going to just use purple. These units down here are going to be meters per second squared. Okay? So at time t equals 0, it's going 6 meters per squared. Meters per second squared. At time t equals 3, it's going 0 meters per second squared as acceleration. At time t equals 6, its acceleration is negative 2 meters per second squared. Then we have at time t equals 9, it's back to 0 meters per second squared. And finally, at time t equals 12, it's 5 meters per second squared. Okay, if we keep reading, it says an additional measurement recorded is that the initial velocity of the vehicle was 10 meters per second. Now what it gave us was an initial velocity. Okay, remember velocity is the integral of acceleration, and its initial velocity was 10 meters per second. So let's read the question. What is the approximate velocity of the car at time t equals 12? So there's kind of a lot going on here. And you could almost say this is an initial value problem, but you're going to see that it's also basically a net change problem. So let's go ahead and just circle what the question is asking. We want to know the approximate velocity of the car at time t equals 12. So how is this a net change problem? Well, if you integrate acceleration on a given interval, you will be given velocity, and that's because acceleration is the rate of change of velocity. And remember that if you integrate something, you're doing the reverse of the derivative, you're doing the antiderivative. So if you take the antiderivative of acceleration on an interval, you're taking the integral of it, and therefore you're finding its net change in velocity. But this question is asking what's the approximate velocity of the car at time t equals 12. So it makes sense. In order to solve this problem, we're going to have to find its change in velocity from 0 to 12, which is just going to be the area under the curve of this chart. Well, if you have a chart, how do you have a curve? Well, the answer is you're going to have to graph it. Finally, we will also use this information that its initial velocity was 10 meters per second. We'll do all of that, and we will figure out what the answer to this question is. Okay, so step 1 is to graph it. So anytime you're finding net change and you're given a chart, you definitely want to go ahead and graph it because you can find the area easily. So you're just going to plot these different points, 0, 6, 3, 0, 6, negative 2, 9, 0, and 12, 5. And again, this is the acceleration graph, okay? So here's these different points that they gave us on the chart. Step 2 is to follow the same steps for net change problems graphically. And remember, to find net change graphically, you just find the signed area under the graph. So we basically need to just go ahead and connect these dots to make a graph. So if we connect them, it looks like a pseudo parabola. It's not quite U-shaped, more like a V shape. We're going to find the area between this graph and the x-axis, and we want to find the signed area. So anything below the x-axis, we will consider negative. Okay, so basically we're just finding the area of this chart, but we're doing the graph. And remember, this is the acceleration graph. If we find the net area, that will give us the change in velocity from 0 to 12. Okay, so we have our first area from 0 to 3, basically, is this right here. It's half of this rectangle. This rectangle is a 3 by 6, which is 18. If we do half of that, we get 9. So that's our first little area. Secondly, we have this triangle below the x-axis from 3 to 9, which we got from these data points right here. the area of a triangle is 1/2 base times height, and we get -6. Let's see if I can zoom in there a little bit. So the second area is -6. Since it's net area, we will make it negative, meaning we'll find the signed area. And lastly, from 9 to 12, we have half of this rectangle. The area of this rectangle is 3 by 5, which is 15. Half of that is 7.5. So the area of this triangle, half of the rectangle, is positive 7. Okay, so if we add all these up, we will get the signed area and we will get the change in velocity from 0 to 12. Now, that's not going to answer the question per se. It's going to get us closer because remember the question was asking what is the approximate velocity of the car at t equals 12. So if we add up 9 plus -6 plus 7.5, that will give us the signed area or the change in velocity. Since again, this is the acceleration graph. It's like going from velocity to position. Same thing, but it's going from acceleration to velocity. So we get 10.5 when you add those three areas. Now here's the thing. Here's the little formula we need to solve the problem. If we take the initial velocity of the car and we add its net change in velocity, that will give us the current velocity. Again, kind of like a analogy, if we have the initial position of something and we add its displacement, we will get its current position. Okay, so we can do the same thing for velocity. Initial velocity but net change plus net change of velocity gives you current velocity. Now we have initial velocity, which they gave us in the problem. Again, they said that the initial velocity was 10 meters per second. We just figured out that its change in velocity was 10.5 meters per second, given this net or signed area. If we add those two up, we get 20.5 meters per second, which gives us the current velocity, which is what we're trying to solve for. Finally, we want to answer this. The best approximation for the velocity of the car at time t equals 12 is 20.5 meters per second. This was required a little bit more. We found the signed area and we had to add it to its initial velocity to get its current velocity. All right, that's it for finding the signed area of the curve of acceleration to get change in velocity, adding its initial velocity to get its current velocity. If you have any other questions about this, let me know.